Hi everybody, this is Ryan and I'm back for another video. This time we're going to talk a little bit about Introduction to Modeling. So we're going to talk about a couple of things. We're going to talk about linear and geometric growth. Those are the two big things we're talking about in this video. Hope you'll find a nice connection between this and functions and the other work that we've done in this course. Okay, so here we go. Here's some definitions. Recursive relationships. A recursive relationship is a formula that relates the next value in a sequence to the previous value. The subscripts of the variable p sub n represent the order of the steps. So an example might be like the sequence 1, 2, 3, 4, and go on forever and ever and ever. So we would say that the next value relates to the first value by adding 1. So p sub 0 is 1, p sub 1 is 2, and p sub n will be the previous number, which we'll call it n plus 1. So it relates to the next value. Okay, let's talk about explicit equations. While recursive relationships are excellent for describing simple and cleanly how a quantity is changing, they are not convenient for making predictions or solving problems. So that's important. That stretch far into the future. For that, a closed or explicit form of relationship is preferred. So an explicit equation allows us to calculate Pn directly without needing to know P sub n minus 1. Okay, so here we go. Here's an example. So let's start off with linear growth. If a quantity starts at size p sub 0 and grows by d every time period, then the quantity after n time periods can be determined using either of these relations. Recursive, p sub n equals p sub n minus 1 plus d. Explicit would be p sub n equals p sub 0 plus d times n. In this equation, d represents the common difference, the amount that the population changes from time n increased by 1. Okay, so this may look familiar to you. If you think about, relate to this formula, y equals mx plus b. We learned about that last video, where m is the slope. I think as we go through this, you're going to see the slope show up. So here's an example. Take a look at this example. The population of elk in the national forest was measured to be 12,000 in 2003. It was measured again to be 15,000 in 2007. If the population continues to grow literally at this rate, what will the elk population be in 2014? So, let's talk about this a little bit. To begin, we need to define how we're going to measure n. Remember that p sub n is a population where n equals 0, so we probably don't want to literally use the year 0. Since we already know the population 2003, let's define n equals 0 to be the year 2003. So p sub 0 equals 12,000. So that's our first value. So p sub 0 equals 12,000. Next, we need to find d. Remember that d is the growth per time period. So again, think about that right there. Growth per time period. That is just slope. In this case, growth per year between the two measurements. The population grew from 15,000 to grew by 15,000 minus 12,000 or 3,000, but it took 2007 to 2003, 4 years to do that. So to figure out the slope, we're going to take 3,000 divided by 4, and we get 750. So that is essentially our slope, is 750. So what we can do is, if we think about p sub 0, this is actually our y-intercept, or our b. So if we just think about the explicit form, which I'm going to recommend you do that, Not too worried about recursive form. We're really going to focus on the explicit form. So we're going to have P sub n equals 12,000 plus 750 times n. Now in this case, where does the 11 come from? Well, to answer this question, we need to note that 2014 n will be 11 because in 2027, actually 2011, so we're going to plug in 11 for our x value and figure that. So there's going to be 20,250 elk. Suppose a 4-year-old boy is currently 30 inches tall and you are told to expect him to grow 2.5 inches per year. We can set up a growth model with n equals 0 represents 4 years. So this time, 2.5 inches per year, that's our slope. And where did he start? 39, that's your b or y-intercept. So our equation is going to look like P sub n equals 39, where he started, plus 2.5 n per year. Now, in 2 years, so at the age of 6, in 2 more years, so we can go 39 plus 2.5 times 2, or 39 plus 5, or 44. So he's going to be 44 inches tall. But what happens if we think about when he's older, like 50 years old? In that case, our value would be 46, so he'll actually be 12.8 feet tall, which is not possible. So you've got to remember that we're assuming that all these models are linear. Well, we all know that as you get older, you don't grow as fast. So it doesn't always work. So you got to use your common sense. When using a mathematical model, we have to consider which inputs are reasonable. So reasonable or common sense. Whenever we exploit or make predictions into the future, we are assuming the model will continue to be valid. So in terms of growth, the model is not valid past a certain point. Okay, so let's talk about exponential growth a little bit. If a quantity starts at P sub 0 and grows at R% every time period, then the quantity after n periods can be determined using these equations. And again, I'm going to recommend that we stick to explicit and not worry too much about recursive. But here's our explicit. Now this equals right here, that should be a plus sign. So that's an error. It should be a plus sign. And we call R the growth rate of growth. So here's an example. Take a look at this example. In 1990, resident energy use in the United States was responsible for 962 million metric tons of carbon dioxide emissions. By the year 2000, that number had risen to 1,182 million metric tons. If the emissions grow exponentially and continue at the same rate, what will the emissions be in 2050? So we're going to use the explicit form for exponential growth. This one right here. So there's our formula. So in 10 years, so we're going to go. So similar to before, we will correspond n equals 0 to 1990. So n equals n of 0 is 1990. As that is the year for the previous piece of data, that will make P sub 0 equal to 962. In this problem, we are not given the growth rate, but instead we are given P sub 10 is 1182 when n is 10. So what we can do then is we can then do some math and we can figure out what our R is. So in this case, we can do the math where P sub 10 is 1182. And we got our original start at 962, and we're going for 10 years. So if you solve that equation, you're going to get R equals to 2.08%. And then what you can do is you can use that to figure out what it's going to be in 2050, which is going to be 60 years, P of 60. So you plug the formula in here, and you get 3,308 metric million tons of CO2. Let's talk about some model basics. Mathematical modeling are tools to represent real-world situations using mathematical language and symbols to simplify, explain, and predict phenomena. These models can be physical, conceptual, or mathematical, each serving a unique purpose in interpreting and understanding real-world scenarios. The process of modeling involves identifying variables, collecting data, and formulating a model that captures the relationship between variables. Models are not perfect representation and should be used with an understanding of their limits and assumptions. The independent variable, represented by the input or the x value. So if you think about the coordinate plane, x and y, x are the independent values. The dependent variable is the y. The y depends on x, and it's usually graphed on the vertical axis. Each point on the graph represents a correspondence between one piece of information from the set of input values with one piece of information from the set of output values. The correspondence, called a relationship, is written in the form of an ordered pair, input and output, and it satisfies a mathematical statement of the relationship between the two quantities described by the equation. A well-defined relation with no ambiguity regarding the output variable is also called a function, which that should be, it passes the vertical line test. Remember the vertical line test? Okay, choosing the right model. When choosing a model for data analysis, it is important to consider the type of change observed in the data. Linear models are most suitable for situations where there is a consistent rate of change, making them ideal for data that shows uniform increase or decreases over time. On the other hand, exponential models are better suited for scenarios that involve rapid growth or decay, as these models are designed to handle changes that accelerate or decelerate at an exponential rate. So linear models typically look like this. Exponential models tend to be curved either this way or this way. Scatter plots are graphical representations of data in two dimensions, typically used to observe relationships. In scatter plots, a strong linear relationship is shown by data that lie close to a line, while a weaker relationship is indicated by more spread out data. So if you have a scatter plot, let's say we have a graph here, XY chart, and I plot a few points. Let's say I plot some points here. Those points are pretty close together, so I could actually come in here and I could draw a line. And those points are pretty close to this line. They tend to fit. Now, if my points are away from the line, then they're not as good, and it doesn't predict as well. So Excel and Google Sheets can help you make scatter plots. Scatter plots help in visually identifying trends, patterns, or correlations in the data, which are crucial for developing mathematical models. Trend lines in scatter plots represent the best fit for the given data, often used to identify underlying trends in the data set. Linear growth occurs when the output quantity changes by a constant rate per unit, resulting in a straight line. So linear models are straight. A linear model can be created and describe real-world situations of linear growth or decay using the slope-intercept form. And that's what I was talking about earlier. Slope-intercept form, slope and y-intercept. The slope of the linear equation represents the rate of change, and the y-intercept represents the starting value. Linear regression is the process of finding equations of the line of best fit. Linear regression can be performed simply by eyeballing a line that minimizes the distance between the output and the input. Between the output and the line. So again, if we have a graph and I have a bunch of ordered pairs on it, close to it, so here's my ordered pairs, I would say that this is a pretty good fit because these points are pretty close to that line. We can see that the overall trend is in that direction. Now, how well it fits. The correlation coefficient, or R, is the value between -1 and 1 that is returned by the least squares method and measures the correlation between the input and the output. In our linear models, a positive correlation, that would be a positive line, would indicate a positive slope, whereas a negative correlation, or less than 0, would be a negative line. Now, the coefficient of determination, or R squared, the value indicates how well the line fits. So if I have my ordered pairs like up here, this one, my R squared was close to 1. Now, if my data is more spread out and my line is not as good, my R squared would be closer to 0. So a perfect fit would be 1. No fit would be 0. So here's some examples. So if you look at these charts, perfect positive correlation. See how all those points fit on that line? So R is 1, R squared is 1. See how these points are not quite as close to the line? So my R squared is a little bit away from 1, it's 0.83. These points are even more spread out, so it's 0.23. These points determine no correlation. There's no line in there. So R squared is 0. And the same thing holds for negative. The strongest linear relationship appears in plots as data that is roughly linear in shape with data points that lie very close to the line. Weak relationships may be roughly linear in shape and more spread out with data points that lie further away from the line. Nonlinear relationships have data points that lie either form other shapes or are randomly scattered across the plot. Extrapolating involves making predictions outside of the known data set, a practice that should be approached with caution. Interpolation refers to making predictions within the data set. Okay, so I hope you enjoyed this video. If you have questions, let me know.